Today.
Correct.
What are we doing? Corrections? Warm up.
See, you could just do it for me, Alan. Okay, so let's go through these and check in. Remember, this was estimating limits numerically. So you were filling in the table to figure out whether or not the limit existed. If the limit did exist, you were determining what it was. What about for the function absolute value of x over x, taking the limit as x approaches 0?
No, D&E.
D&E, why is it D&E?
Because they don't match up.
They don't match up on either side.
What limits don't match up?
From the left and from the right.
Right.
Right, the left-sided limit and the right-sided limit, they both exist, right? The limit as x approaches 0 from the left would be -1. From the right would be 1. They don't equal each other, so the two-sided limit is D&E. Wonderful. What about for this rational function, as x approaches 3, g of x is approaching, is it? 1/6. 1/6, or if you wanted to put the decimal as that point.
I got
1/6 repeating.
0.16 repeating.
Yep, 1/6 repeating. Would be fine because this is estimating numerically, right? So you could have said 0.16 repeat, or if you had put 0.16, you would have done that. I guess that works. Okay. Piecewise function, it's a good one too. So limit as x approaches -2. Why?
And then the other side goes to 4. So 0.00.
But this is different.
Yeah, it's just different. Left and right are just different.
It's just different.
Just real different.
What's it's just? What's the it?
The point of
The point of interest.
no. The value at which the graph approaches as it reaches the target x, which is the limit. It's different on each side.
Miss Dorset's just like, what?
How about the limit as x approaches -2 from the left would be 4,
4.
and the limit, it would be 4, and the limit as x approaches -2 from the right would be 0. So the one-sided limits don't match.
Did I use the wrong match with that?
Well, did you
Well, Alan
check
was
in
just
the
cooking.
piecewise?
No.
Plus,
Oh, was this like I think I had something on the graph?
he was cooking, but like, no one
No,
was
the table,
hungry.
like if you had typed in the piecewise,
Whoops.
right? If you had typed in the piecewise, then you could type that in and you could have gone to the table.
Oh, I thought we were supposed to decide which equation to use.
You could do that too, but from the right,
Don't forget to get your.
would have been plugging into this one.
Oh, right, I need to get mine too.
Because you want to be directly to the right of -2. Okay, and the last one, so same function, but as x approaches 0, the limit of h of x would be 2. Are we okay with that?
Yep.
Yep. Okay. Any questions? So we have introduced what it means to take the limit of a function. We have talked about estimating limits numerically and graphically. So in section 1.3, we're going to start getting into like evaluating limits and using limit properties and algebra. Good? Okay. We're ready to move on? Cool. Skibbity boo bop.
Oh my god. Is this how the seniors felt last year when you said chat?
Well, they were the ones that told me to say it, remember?
You didn't tell me to say Scooby Doo.
Oh yeah, I remember when Mr. Kim asked Trevor and I what it was. Remember while we were bowling?
Oh yeah. If you're gonna say anything, don't say Scooby Doo up. Say that's so Sigma.
What does that mean?
I don't know.
Absolutely nothing.
I really don't.
Absolutely
It
nothing.
means more than.
Sounds
Scooby-Doo.
mathematical, doesn't it?
Yeah.
Yeah.
That's so it's like
Bro,
that's so
For
some.
no reason.
That's
I
so
was like-
Sigma.
Dude, I was like, and the TA was like showing us a graph, and the attribute was like sigma. And he said like sigma.
What?
Okay, section 1.3, evaluating limits analytically. So we can evaluate limits analytically either applying limit properties using algebra, using calculus eventually, like using derivatives in order to help us evaluate a limit. But in section 1.2, we learned that the limit of f of x as x approaches c does not depend on the value of f at x equals to c, right? We talked about the 3 different cases whenever the limit exists, right? So if the function is continuous at c, like using what we know as our definition of continuity, then the limit will match the function value at c. But also if there's a removable discontinuity, right? So if either the function value doesn't match the limit, but like the function still is trending towards one specific value, we say the limit exists, or if the function is just undefined at whatever x is approaching, but it's still trending towards a value, right? Are we okay with that? Okie dokie. So there are times when you can evaluate the limit of the function by direct substitution. And the time that you can do that is whenever it's that first case. So if the function is continuous at that value, then you're able to just use direct substitution. Direct substitution will be your go-to. Like it's what you'll try first. If that fails, then you dip into your toolbox, right? Like with what you know in order to evaluate. These are all the properties of limits that we'll need to use. And they'll feel kind of familiar, even though these properties are for limits. But like if we think about like our knowledge of functions, do you guys remember in pre-calc? What was that? Chapter 1, so like the very beginning of last year, we talked about like creating functions from other functions, like by performing different algebraic operations, like adding, you could create a function from adding functions together, from subtracting, multiplying, dividing. So I kind of want you to think about these functions that we're thinking about taking the limit of from that perspective of we've created functions from other functions. Am I switching?
Why?
I don't know. The internet says I'm either tired, stressed, or too much caffeine. Probably all the above, you know. But it's been switching since the last week. Okay, what are we talking about? What are we doing? Where are we? Am I recording?
You said something about last year functions combined.
Oh, your composite.
Yeah.
Right, okay, so this first property, I want you to think about taking the limit of a function that is like a sum of two functions. For example, a polynomial function that has multiple terms. So like x squared plus x, like y equals x squared plus x. You could think about that as being one function, right? It's a polynomial function that has two terms. Or you could think about it as being a function that's created from adding two functions together, like x squared being one function, like being f of x, plus x being g of x. Does that make sense?
Yeah.
Okay. So whenever we're thinking about taking the limit of a function that is a sum, you can think of as a sum or difference of other functions. You can think about just taking the limit of each part of the sum or difference. Okay. We remember what scalars are?
They're non-vectors.
That's true. Because they only have
Direction. No. Magnitude. No.
magnitude, right? They're just
There's
real.
one of the two. One of the two.
Just a number, just a real number, a constant, okay? So basically, if you think about having a function that's being multiplied by a constant, for example, like 2x squared, you could think of that 2 as being a scalar. We're you can think about pulling that constant out or pulling that scalar out and then taking the limit of like the function. Does that make sense? Okay. Multiplication, so if you have a function that you can think of as being a product of two functions, you can think about taking the limit of each factor. And it says as long as these limits exist. If one of those limits doesn't exist, we'll talk about that in a few minutes. And then if you think about having like a function that's a quotient of two functions, maybe like rational functions, right? Ratio of two polynomials. You can think about taking the limit of the numerator and the limit of the denominator, unless the limit of the denominator is 0. In that case, the limit would be dne. Power rule, which actually kind of goes into, is like a subset of composition rule. But power rule is a little bit easier to understand at first. So like let's say that we had like the quantity x plus 7 raised to the 8th power, and you're taking the limit. You could think about taking the limit as x approaches a number of x plus 7 and then raising that value to the 8th power. Or like square root of 2x plus 5. You could think about taking the limit as x approaches a number of 2x plus 5 and then taking the square root of that. Composition. This is the one that's like a little bit tricky. And the problems that would show up that relate to this property will feel really kind of contrived. Like, I have an example of one of them on here. This is the one that's kind of like wrapping your brain around might take a second. I wouldn't stress about it though. Like, we're not going to get too hung up on it, okay? And I'll show you, like, if it were to happen, there's like a very small number of problems where it might show up, or types of problems where it might show up. So note, in general, the limit can be taken of each piece of an expression. In general, if the limit can be taken of each piece of an expression, then the results of those limits may be combined using the algebraic rules of the expression. Okay, so we are going to use limit properties. We don't know what the rule is for f of x, g of x, or h of x. We are just given the values of these three limits for some constant a, and we are going to determine if the limit exists. If the limit does not exist, then we are going to explain why. Are we ready? Now, you have some options on how you want to show your work here. So, like if we're trying to find the limit as x approaches a of f of x plus h of x, this uses that first property, right? The sum property, where we could think of this, and you can write this out if you would like. The limit as x approaches a of f of x plus the limit as x approaches a of h of x. And then you go, oh, hey, the limit as x approaches a of f of x would be -3. And the limit of h of x would be 8.
Oh my God, Jack,
So we get 5.
what's your wish, Jack, about this?
I am comfortable with you doing these steps in your head. So if you looked at this and you were like, hey, that's 5, that's fine. You don't need to show demonstrating the property. It's being applied. You can, but you don't have to. Same thing here. So limit as x approaches a of f of x squared. Now, this is equal, this is that power property, right? Which means that this is equal to the limit as x approaches a of f of x being squared. You can write this out. The limit of f of x as x approaches a is what? -3. you can also just say this equals to 9. My minimalists. Right on.
Yep. If there's a 0 in the denominator, for these, is it D?
You're going ahead.
Huh?
We're on C. We're on C.
What are you doing?
Did you
So
say
what-
right
talking about
on or right
discriminants.
on?
Why don't you guys try C? So cube root, right, can be thought of as an exponent. So you could apply the same property, that power property that we just applied. So take a moment, and then why don't you check your answer with someone who's sitting near you?
Let's do that.
The cube root of h of x.
2.
2. Right? Because it ended up being the cube root of 8, which is 2. Okay, this next one's kind of interesting. This is a quotient, right? So this is, you could think of applying that quotient property. The limit as x approaches a of 1 over the limit as x approaches a of f of x. If we think about the function y equals to 1, what's the graph of that look like? Yeah, it's just a constant function, right? A horizontal line. So as x approaches any real number, y would be approaching 1. So it'll always be 1. So 1 over, and then the limit as x approaches a of f of x is -3. So this limit's -1/3. All right, why don't you guys do E? E. Have we done E already?
Zach, we forgot to check our answers.
Oh. C, I got 2.
E. Indeed.
For D, I got
Pretty E, right? For E.
E.
for D, I got 2.
Sports.
So I haven't.
It's
yeah.
so game.
You're running away with this.
Are we? Am I going too slow? Am I going too slow?
No.
Not for me.
All right, what do we get for the limit as x approaches a of f of x over h of x? What do we get? Yeah, -3/8.
Well, this morning I saw Miss Petrarska across the hall and I like whispered like, Miss Petrarska, and her head turned to me.
Okay,
and I
that's
was
like kind of
oh.
weird. Like,
What? Well, I didn't want to. I was trying to get her attention. I didn't want to yell like Miss Petrarska, so I was just like keeping the excitement inside.
That's
That's like
like-
Miss Petrarska. And her head turned to me and she saw me, and I was really embarrassed.
Wait, if you're calling getting her attention, why would her head not turn to you?
No, I wasn't trying to get her attention.
Oh.
I was just
why
trying
did
to
you just say her name?
just to myself as like that's exciting, you know.
What?
It's
Alright.
Again, we are recording right now.
Oh, I'm sure Bailey Drew already himself.
This is Michael's confession.
Okay. Let's do this. Let's talk about this one. Okay, so if we were to apply that quotient limit property. Well, ooh, what am I doing?
Stay hydrated.
What happens?
Oh,
Done work, because it's 0.
it's not in the
You
dictionary.
do like D and E or something?
Well, you get -3/0. And the thing is, based on the limit property, right, the denominator, that limit in the denominator can't be 0. So you're right. This does end up being DNE because, get used to that a lot. We're always going to go, because the limit as x approaches a of g of x is equal to 0. Why don't you guys give G a try? See what you get for G.
Give me a second.
There's multiple.
What are we
There's
doing?
multiple properties being used. Have you already done it?
No.
That sounds like that. Or having.
Okay, so like if you were thinking about applying the limit properties, you're like, oh, it's a quotient. I'm going to apply the quotient property. Oh, I can pull out that scalar in the numerator.
What about that vector?
There's no vector here.
Oh yeah.
And then the denominator. You're like, okay, I'm taking the limit of the denominator. Oh, there's a difference.
What's the difference?
You just copied the
Sorry.
question.
You tell me.
I'm actually glad I'm recording, so it's on the record that I wasn't trying to be creepy when I was recording that. That I was genuinely just like trying to hold it.
Direction and magnitude. Oh yeah. Oh yeah.
Okay, so what do we end up with? -6 over, because 2 times -3 over.
The negative cancels out to a positive, so it's 8 plus 3 is 11.
Oh, yes.
Quick math.
So -6 over 11.
Did you watch the new Despicable Me movie?
I did not, but I did see Inside Out 2.
Wait,
My son.
I like the new Despicable Me movie.
Is this Super Minion one where they like?
Oh yeah, the Mega Minions.
Yeah.
Okay, are there any questions at the moment on limit properties? Are we okay so far? At least with that type of problem? Okay. So now we're going to do the same sort of thing, but
So the last number 6, the composition one, we haven't done that yet, right?
What?
The composition limit property. No, the
Oh,
right,
no.
number 6.
you're going ahead of me.
This one we haven't done, right? No, the one we.
Oh, correct. Well, kind of with the power, but right, we haven't used that one directly yet.
Okay.
We will, though,
Yeah,
in a
just-
second. Okay, just hold the thought, Alan, hold the thought. Okay, so limit as x approaches 2 of f of x plus g of x. You can think about taking the limit of each part of the sum there. You just have to read the graph in order to evaluate the limit. So, the limit as x approaches 2 of f of x would be... 2. Do we see that?
Yeah.
Okay. And then the limit as x approaches 2 of g of x would be...
0.
So our limit is just 2. Okay.
21.
That's kind of anticlimactic.
Sorry.
How do you get more action in this?
So then applying the limit property. So for this one, you could think about pulling out the 2, then taking the limit as x approaches 1 of f of x. Are we okay if I skip to just thinking about what the limit is? Or do you want me, is it helpful for me to write out the property being demonstrated? Are we ready for this?
I'm afraid.
Yes.
Sure. Okay, so then we'll have 2 times the limit as x approaches 1 of f of x minus 3 times the limit as x approaches 1 of g of x. So then looking at f of x, as x approaches 1, what is f of x approaching? 1, okay. And then we go over to g of x. As x approaches 1, here's the thing. This is meaningless. You can't just write this on your paper and be like, oh, it's D&E. What this tells you, right, this is a meaningless expression. The property doesn't hold because part of that expression has a limit that doesn't exist, okay? So we have to kind of dip back into our toolbox. What must be true for a two-sided limit to exist? Because this is a two-sided limit, right?
both sides of the limit have to agree with each other.
The one-sided limits both have to exist and be equal to each other. So I'm actually going to get rid of this, later gator, and I'm going to examine the one-sided limits. So I'm going to say, okay, the limit as x approaches 1 from the left of 2 times f of x minus 3 times g of x. Okay, so 1 from the left would still be 1, so we'll have 2 times 1 minus 3 times, the limit as x approaches 1 from the left is 2. Okay, so 2 minus 6 will be negative 4. And then the limit as x approaches 1 from the right, that'll still end up being 2 times 1 minus 3 times, but the limit as x approaches 1 from the right of g of x is 1. Good. So we end up with negative 1. So we can say that the two-sided limit, or here I'll just copy and paste that, huh? That's probably faster. Can't be? Paste. We can say the two-sided limit is dne because the one-sided limits aren't equal to each other.
Is it possible that, like, let's say, the limit of f of x from the left is 2 and from g of x is 1, and then they swap, and the limit's the same, so it does exist?
It could.
Even though none of them have, like, an actual limit?
I would have to think about, I can't think of an example of that happening.
Like, what if limit
Oh,
of
I'm
f
just
of x is
gonna put it on
1,
the test.
and the limit of g of x is
Yeah, like two
2,
jumps.
2 and 1 and 2, and then right side it's 2 and 1. Or no, what if? Yeah, 2 and 1.
Yeah,
So they both be.
and it's if it were addition between the functions, right, which is commutative. Yeah, I think that could work.
Yeah.
Can we draw that out? I don't know.
Or multiplication.
Or multiplication. Anything that would be commutative, right?
Yeah.
So
Okay.
he's saying, like if we had two graphs that were jumps, but they like were opposite jumps, like the jumps were just like opposite values of each other. Is that what you're saying?
Yeah.
So then, like if you're thinking about taking a two-sided limit, it wouldn't be equal. But then if you were to take the one-sided limits, the sum would end up still being the same. So the one-sided limits would be equal to each other.
Yeah. That makes sense.
So, like you're saying, like if one of the limits was
That's a good example. I think here,
the,
kind of draw a picture here.
the people who were recording probably won't see it, but
That's okay. Maybe I can edit this out.
Great.
I just remember because when I was watching the Link video, you started drawing something on the board, and I was like, oh,
Okay, so let's say let's do something simple. So let's say we had like, we'll say this is 1. So like that, and then over here, like that, and then we want from, like that. wait, no, I want it flipped, right?
Yeah.
So I want from this side to approach 2. So something like that, and then, I don't know, what do you even do horizontal, right? Where then if we were taking the limit as x approaches 1, call this f, call this g, of f of x plus g of x, right? If you applied that property, but it's a two-sided limit, you'd be like, DNE plus DNE, it's DNE. Or maybe it's not. But then if you were to take the one-sided limit, so if we thought about the limit from the left, so then we would get 1 plus 2, which is 3. And then if we take the limit as x approaches 1 from the right, right? So then we get 2 plus 1, which is 3. So since the one-sided limits would be equal to each other, the two-sided limit would exist and also be equal to 3. That was a good example. Did we follow that? Is that helpful?
Yeah.
Okay.
That was actually very helpful because I wasn't visualizing that before.
Is there a way that I could no.
Wait, are you screen recording?
Oh, you can open the camera on your iPad.
Yeah,
Like,
I can just.
And just show, because I'm screen recording. Say hi, everyone.
hey.
Okay. This is the example we just talked about where the two-sided limit would exist. Boop.
Oh.
Okay, cool. Okay, so let's check out C, the limit as x approaches 0 of f of x. Why don't you guys check that one out on your own? But that would end up being the limit as x approaches 0 of f of x times the limit as x approaches 0 of g of x. What is the limit as x approaches 0 of f of x?
0.
And then what about for g of x?
No clue.
Maybe
I don't know,
like
1.6.
something like that, right?
1.6.
Like yeah, sure. But because that's times 0, it's just
Doesn't
going to
matter.
be 0. If that were DNE, like if the limit as x approaches 0 for g of x was DNE, then that would be something we would want to examine. Okay. Quotient. So if we take the limit of the numerator and the limit of the denominator, oh, what happens? Ruh-roh, it is DNE because, why is it DNE?
The denominator is 0.
Yeah, because the limit as x approaches -1 of g of x is equal to 0. Whoops. Whoops, whoops. Look at this one. That's different, right? So the limit as x approaches 2 of x cubed times f of x. Well, that's a function that's created from a product of two functions. We just know what the rule is for one of the functions. Or one of the factors. Factor functions. Function factors. Okay. Now, what would the limit as x approaches 2 of x cubed be? 2 times 2 times 2, right?
Yeah.
8.
8.
And x cubed, remember, chair function, continuous function, right? You could use direct substitution. And then the limit as x approaches 2 of f of x is 2. Oh, that's why you said 16, Zach. I'm sorry. I thought you were saying, sorry. I thought you were saying the limit of as x approaches 2 of x cubed is 16. There we go. All right, are our brains like warmed up? We're ready for the composition one? Yeah. Now, before we get into demonstrating the limit property, which I'm going to copy and paste down here so we can reference it. Let's think about when we have a function that's created from composing two functions, right? So like if we have a function f composed of g of x, okay? And we're thinking about inputs and outputs, right? If we are thinking about taking a value from the domain of this function and inputting it, we're going to end up inputting, and g of x will be evaluated first, where then f is evaluated for the outputs of g of x, like values that are in the range of g of x. Yeah?
Okay.
You're with me so far?
Yeah.
Okay. So, when we take the limit, we're going to first think about taking the limit of this inside function.
Okay.
You follow that? Okay. So the limit as x approaches 1 from the left of g of x would be 2. But here's the thing. G of x is approaching 2 from below, right? Like values that are less than 2, which on a number line would correspond to values to the left of 2.
Yeah.
So that means then when we think about rewriting this limit, we're going to think about taking the limit. Well, there's two ways you can think about this. You could think about taking the limit as g of x approaches 2 from the left of f composed with g. Right? Like values that are less than 2, we're coming from the left of 2. Or to match up with what the property says, you can write this as just the limit as x approaches 2 from the left of f of x. Now, if we're not going to spend too much time on this, and I'm going to give you one additional example here. But let's say that the graph was approaching 2 from above. Those would be values that would be greater than 2. Then we would say, we would rewrite the limit as x approaching 2 from the right, because approaching from above, like the function value approaching from above, on a number line would correspond to values to the right. If the function, so like let's say that you're taking the limit, like a two-sided limit of a composite function. If the function were approaching from above and below, then you could rewrite still as a two-sided limit. So it just depends like which direction the graph is approaching the value from. Okay, let's finish this one. I'm going to give you one more example. So the question?
Kind of. If it says like 1 from the right, instead of 1 from the left, would it still be the same thing because it's approaching? Oh wait.
It would be 1 from the left.
Okay.
Good question. Okay, so let's finish this. So now we're thinking about as x approaches 2 from the left for f of x, we would get 2. Are we okay with that? The extra example I'm going to throw on here is the limit as x approaches 2 of g composed with f. So thinking about first, as x approaches 2 for the function f of x, it was a two-sided limit. So as x approaches 2, or the limit of f of x as x approaches 2, ends up being 2 approaching from below. Now, if we were taking that two-sided limit and let's say instead of this part, it was like something like this, then we would rewrite the limit as x approaches just 2 of g of x, the outside function. If both sides were coming from above, then we would end up rewriting as limit as x approaches 2 from the right of g of x. Right, values greater is from the right. Values from that are less than would be below. But this ends up being the limit as x approaches 2 from the left, because the graph is approaching 2 on f of x from below, of g of x. And then, as x approaches 2 from the left, oh, why did I rewrite it? I didn't even rewrite it. What do we get? What's that limit? 0.
Wait, do you need to do the left and right side, or can you just do?
Okay, Jake asked this question earlier. For this one, if you wrote this step, yes, you have to say from the left. If you didn't have from the left, it would be incorrect. If you, though, just went from here to here, I would have nothing to take off, because you're not required to write this step.
Wait, sorry, I might have missed the explanation, but like, why are you required to have that step again?
You don't technically have to have that step, but if you write it, you have to say 2 from the left, because g of x is only being evaluated for values that are to the left of 2.
Oh, why?
Because if you look at the function f of x, right? So g is being evaluated for values in the range of f of x.
Right.
Like the range of f of x is the domain of g of x, right? And so if those values are approaching 2 from below in the range of f of x,
That's true.
then that means that those values, like thinking about inputs into g of x, then would just be approaching from the left.
Yeah.
I probably would not, if I put a question like this on an assessment, I would probably not put one where you could get lucky if you just left off, like if you didn't think about it.
Yeah, so you actually have to.
Like I would probably put something where you're actually having to think about what it is. But then again, you have a 50-50 shot, right? Or no.
Yeah.
What?
Can we scroll back up to letter F?
Yeah. For here, so thinking about taking, because when you evaluate a composite function, right, like you're inputting values and then they have to pass through that inside function first, and then you end up evaluating the outside function for the output values of the inside function, right? Like the range of g of x ends up turning into the domain of f of x. So we kind of think about passing through that, so we think about taking the limit of the inside, figuring out what that would be. So then we're thinking about, maybe this is where this would be helpful. So like, since this is the input,
Yes.
you're thinking about taking the limit as g of x approaches 2 from the left of f of x. Right, so as the y values here, or of g of x, are approaching 2 from the left, f of x is approaching 2.
Oh, okay, wait.
This is when it might take a little reflecting and processing time.
Okay.
But we also don't want to spend too much time on it. It's not like that big of a deal. I'll find some more, we'll do some more examples next class on that one.
Okay.
Okay,
Thank you.
no problemo. Evaluating, so direct substitution is your go-to. You're also usually using properties of limits. So direct substitution won't always work, but as long as the function is continuous at a point, you can use it. So why don't you guys go ahead, A, B, C, D, E. Is there an F? Nope. A, B, C, D, E. Up, Trig. Woo! Go ahead and evaluate all of these. And then check your answers. If you are wearing pants, you have to check your answers with somebody that's wearing shorts. And if you're wearing shorts, you have to check your answers with somebody that's wearing pants.
I'll check with Jay. You can check with Jay as well.
Yeah.
Oh wait, I'll check with someone else then, because they can't check. Wait, Aaron has to check with everybody.
Yeah. I'll roll up my pen.
You'll roll up your pants.
You guys, just do them and find someone to check with. Talk to new people. There are 5 of you in this room right now.
Wait, why is there trig?
There's nobody else.
Oh no, I forgot my unit circle.
Oh, sin x. Oh no.
Do you remember your unit circle, Ms. Dorset?
I think after a while it gets burned into your brain, doesn't it?
Hey, do you guys remember like last year when I was like, hey, like you really need
I
to
do
know
remember
this
it.
because
I
you're
do
going to
remember
need
it.
to
Sign
use it next
0.
year.
Like
it's not
wait, was it?
it's not something that you can just like learn,
Sin is 1.
use it for a
Sign
test, and you'll never see it again.
Root.
0!
No, sin is 0, that's
That
one.
is 0.
Root 3 over 2.
Root. No, that's up here.
Alright, you
1
should be
half.
evaluating
Root 3
using
over 2.
direct
Oh, yeah, yeah, yeah.
substitution.
Root 3.
Come on.
Oh yes.
Oh no.
How do I do this?
Chilling, bro. Chilling, bro.
Love and chug.
Plug it and chug it.
Whoops.
Jay, what'd you get for the first one?
I got,
4.
yeah,
I gave 4.
I got all the above.
You know what I should have done? You have to check with somebody that's not in your grade.
What?
Oh,
What?
wait.
Are you serious right now?
There's an imbalance.
You guys are like insulting to each other that you're like, no, I don't want to talk
I don't want
to
to
them.
work with Michael and Zach.
Yeah, they hurt my feelings.
It's a joke.
I'm just playing with you guys.
Michael, what'd you get for number B?
Oh, I'm so glad you said
Who got C?
Number B is crazy.
Who got C?
Who got?
Who got
Wait. Oh, yeah.
I'm not at it.
Um,
Sorry, Jay.
Wait, cotangent is what again?
Yeah,
What is
yeah,
it?
yeah.
Wait, cotangent is what
You're
again?
confused.
How do you do this?
You just put it in.
7 minus x to the power of
Okay.
So- to solve this, you need to
You
figure
would
out
still
what
need
the
to
y
have-
values of f of x are.
What did you get for
Wait,
this?
you would
Wait,
still have, so if you were
what's
trying to
the
rewrite it
versus
this way, you
one?
would still have the f of x inside there.
Oh, I did my arithmetic
Because
wrong.
you're evaluating g at f of x. like using this
Well,
notation.
who's gotten to E?
This is, if you're thinking,
Okay, R.
yeah,
R.
like
Wait,
this.
what's pi over 4 again? Is that root 2 over 2?
But 2
Doesn't
from
matter,
the,
like,
two
four.
from the left.
What do you mean?
Oh, cotangent pi over 4.
Bro, what?
Oh, shoot.
Alan, what are we doing?
Oh, my applicant died.
Oh wait, I can just put that in the calculator.
Because I feel like.
Because the values are
Just
only
remember
coming
tangent.
from the left.
Tangent of pi over 4. Pi over 4
Because
is.
the
is
graph
like
of
this,
f of
right?
x, as
Tangent
x
is sine over
approaches 2,
cosine.
the graph of f of x is
Cosine
only
0.
approaching
Alan,
0
stop
from the
talking.
left. So like there's not values to the right. Right, there's no values approaching from above.
What's 9? 9 minus.
Alan, what is
7 is 9.
Oh, just plug it in there? I thought it was like
So.
root 7 minus
Plug in.
root 2.
So you
Oh,
can't
is it?
consider
Yeah.
inputs
Put it in.
from the right.
Put it in, bro.
Are you sure?
No pause.
Pause.
No pause.
So why do you guys like.
Sure.
What this is.
I just don't. Sure.
Shut up.
Why is it
Pi
like
over
approaching
2
from the left
is
the limits
80
always
degrees.
like I don't know.
So it's
No, because you're
Okay.
thinking about.
Alan, just put it in your calculator.
It's again.
So if we're talking about
I'm
the
done.
limits, G because of f of x, right?
No, it's not.
So like
It's
the
1.
inputs
No.
Oh, it's
for
0.
x
It's
approaching
1.
2, that's
Yes,
considering
it's
from the
1.
left
So
to right.
sine pi over 2 is what? Alan, you
And
cut it
it'll pass
wrong.
through f of x first. So we're thinking about the
Sine
x
pi over 2
values
is 1.
being inputted into
So
f
it's just
of
pi over
x.
2.
Pi over
Right.
2.
No, it's negative 1.
On both sides,
Alan,
f
what?
of x
Pi
is
over 2.
approaching
Sine of
positive
So,
2. Maybe
you
it would
have
make
this,
sense
and
if
then
I
you have
used
this.
like
This is
half
pi over
the
2. The
different
90
values,
degrees is
like,
pi over
say it's
2.
approaching
Oh, wait.
One.
Oh, I
If it's
see.
approaching
Pi over
3
2.
from
Yeah, just
below,
pi over
Times
2.
1 is 1,
right,
right?
those are all values that
No,
are
one.
less
No,
than
it's 1 times pi
Pi
over
over
2.
2.
Alan, bro, you're wrong.
Alan, you're asking.
Yeah, I know.
So
I'm
then
not
you're
performing on
evaluating
two.
Alan, you're selling.
the
Pi over
outside
4 is sine over
portion
cosine.
G
Just 1.
for only
D is
values
just
to
one.
the
Yeah, okay.
left,
Boom. Zero done.
because there's not values.
I tried to use it, you have hands on.
Oh, wait, Michael,
Right,
Michael,
there's no
Michael.
function
What's that?
values
Can I use the restroom?
No.
above 2.
Can I check
The
the
greater
answers?
I actually listening to Ms. Darcy's explaining, so I don't have any.
I don't know if I.
Yeah.
Jay.
Okay.
Think about it for a little bit, or think about it
1
later.
and
I will
2.
move on from here for now and do the direct substitution.
Okay.
And we can talk about it more next time too.
Alan,
Where's the answer?
Okay.
Do we need to like just kind of know what these functions look like, or can we like plug them in? I mean, I generally feel like can we plug them in?
No, direct, so all of these ones, you're using direct substitution, which means you don't need to really think so much about applying the limit properties. It's not wrong to, but those are extra steps you don't need. Like you're just plugging 1 in for x and simplifying,
Oh.
Okay.
right? Because you're taking the limit of x squared minus 9 over x plus 1. So you plug it in, and it's going to be, you're going to get a value because the function value will match the limit value.
Okay.
Skippy for the
What are we saying?
Ohio wrist.
Okay. Did you guys already check your answers?
Yeah.
We're not done. What are we doing?
Just stretching.
Okay. So like for A, okay, can we sit down? What do we get for A, you guys?
Negative 4.
Okay. And what do we get for B?
Negative 4.
Also negative 4. How about C? Not plus or minus, you're not solving anything, right? So it's implicitly just positive square root of 7 minus x. There would have to be a negative in front if it were the negative square root. Right, the plus or minus only comes from solving, like if you have x squared equals to 4, well, x could be positive or negative 2, sorry. D. 1, good job. Right, because sine and cosine are the same at pi over 4. And then what about E? What is it? Pi over 2. Because sine of pi over 2 is 1. Okay, if we've forgotten our unit circle, you guys, we need to like brush up on that real quick. So like I was saying earlier, direct substitution is going to be your go-to. Unless you are dealing with a piecewise function. Like if you're taking the limit of a piecewise function, you want to be careful. Because if the limit that you're taking is x approaching a number where the domain switches, then you want to think about one-sided limits. You don't want to just jump to, hey, I'm going to plug in wherever, like based on domain. Does that make sense? Because there could be like a jump or something because of like the way the domain restrictions are piecewise. So if you just have like a normal function, algebraic or trig, exponential or logarithmic, right? You're just going to first try direct substitution. If direct substitution doesn't work because you get 0 over 0, and we have experienced this before, do we remember experiencing 0 over 0 before?
No,
Maybe 2 over 0.
I don't.
Well, 2 over 0 would result in the limit being d and e, but we'll talk about that more in a second. So if you use direct substitution and you get 0 over 0, it might be because there is a removable discontinuity, also known as a hole.
Oh.
Not just for rational functions, because rational functions is where we saw this. When we studied rational functions, right? And if there was a common factor in the numerator and denominator that canceled, you knew that that common factor, right, if it was like x minus 2 was the common factor, that x equals to 2, there was potentially a hole, because a function looks like the simplified version of its equation, like its graph looks like the simplified version of its equation that has the domain restrictions of the original function. This sounds familiar, right? Okay. So, if you try direct substitution and you run into 0 over 0, which is called an indeterminate form, and you do need to know this vocabulary. There are other types of indeterminate forms that we will eventually run into. For now, 0 over 0 is the only one we're dealing with limits. And that tells you that you have more work to do because the limit might exist, it might not. But the reason the 0 over 0 is happening is because there is a common factor in the numerator and denominator that when you're substituting whatever that number is that x is approaching, there's a common factor that's causing that 0 over 0 that you have to try and uncover and cancel, right? So you have to try and eradicate. And to do this, there's different algebraic strategies that you can use, and we're going to go through. Before we do that, though, just to kind of show you an example of whenever 0 over 0 happens and the limit exists versus it doesn't actually exist. Okay? So you never, with direct substitution, you never say that the limit is equal to 0 over 0. It's meaningless. Just like you wouldn't write that the limit is equal to like 2 times d n e. Like that doesn't mean anything, okay? But you should always with limits first do like a mental direct substitution. I like to put a note of like, oops, that's not what I was trying to do. I like to put a note of like 0 over 0 to remind myself that I ran into indeterminate form. Okay, so both of these are rational functions. They look sort of similar. They are both rational functions. Do you guys remember when we studied rational functions and we were trying to identify characteristics about rational functions? We tried simplifying the equations, right? Like the rule for the function by factoring and seeing if there were common factors. So like in this first limit, we could think about factoring the numerator. And I know that it's x minus 2 that is causing the 0 over 0. Because when we substitute in 2, that's when we're getting the 0 over 0. When you do the algebra, you need to keep the limit notation. Notation matters. So x minus 2, x plus 2. Okay. And from here, we're like, oh, hey, now we can cancel the x minus 2's. And we'll have the limit as x approaches 2 of x plus 2. Now, here's what should feel familiar from last year. If we graph that rational function, the graph just looks like y equals to x plus 2, the simplified version of that expression. But if we go to where x is equal to 2, right here. Oh, I saw it, right? At x equals to 2, it's undefined. So the graph looks like the simplified equation, but has the domain restriction of the original equation. Okay? Now from here, we're like, oh, well, we can use direct substitution here. 2 plus 2 is 4. So the limit does exist. Graphically, you guys know from your prior knowledge that there's a hole at x equals to 2. There's a removable discontinuity. At x equals to 2. Versus over here, we don't have to factor. The work's already been done for us, right? This x minus 2 can cancel with one of these. So then we have the limit as x approaches 2 of 1 over x minus 2. When we use direct substitution here, we end up with 1 over 0. You're like, what's that mean? Well, we kind of know from limit properties, right? If 0 is in the denominator, when we've evaluated the limit, but the numerator is something else. The limit is DNE, but also, you guys are familiar with this function. 1 over x minus 2, y equals 1 over x minus 2, right? Like, you guys are familiar with the graph of 1 over x. What's that minus 2 doing to that graph? Shifting it to the right 2. So what occurs at x equals to 2? What type?
Vertical.
There's a vertical asymptote, which means as x is approaching 2 from the left or the right, the function is either increasing or decreasing with that bound. Now this is a graph that you guys are so familiar with. Like if I asked you the limit as x approaches 2 from the left, you could tell me that the function is approaching negative infinity, and you would be able to say it's equal to negative infinity, right, that limit. And from the right is approaching positive infinity, you would be able to say that. But this is a two-sided limit. You know, because of your prior knowledge, that from each side they're approaching different infinities, so all we can say is DNE. Okay, so there's a vertical asymptote. Which, remember, is a non-removable discontinuity. Okay, so two limits where we ran into indeterminate form for both. One, the limit did exist, one, the limit did not. One had a removable discontinuity, one did not. One had a non-removable. Just stay with, we have 8 minutes left, you guys. We can do it. So I have some little names for the different algebraic methods that you might want to use to try and resolve the 0 over 0 issue. Like if you have a rational function, you guys are familiar with that, we're going to factor and divide out, or FODO. You will not find FODO in any textbook. But you guys are familiar with this one. I'm going to go through just this first one really quick, and then I want to maybe try the next one. So like if you try direct substitution, you're going to run into 0 over 0. You can do a mental check of that. Then we take the limit as x approaches 0. I'm going to factor x squared out of the numerator. Notice I still have the limit notation. X squareds can cancel, so we're taking the limit as x approaches 0 of x squared minus 5. And then now we can use direct substitution again. It's only when you go to use direct substitution again that you can drop the limit notation, right? So 0 squared minus 5 is just going to be minus 5. Just a few more minutes, you guys. We can do this.
Can you say that again? What?
When you go to use direct substitution, after you have gotten rid of what's causing the indeterminate form of 0 over 0, like you've gotten the common factor to cancel, once you go to use direct substitution, that's when you drop the limit. Can I skip this one for now?
Sure.
Just so we can kind of introduce RATCON. Okay. RATCON. So just if you run into indeterminate form, and you're like, I have to try and uncover a common factor of x minus 3 in the numerator there. You can try and rationalize the numerator in this case by multiplying by a version of 1 that is the conjugate of the numerator in this case. Right? The conjugate of like a plus b would be a minus b. So in this case, the conjugate, and we know we want to try and get rid of this square root, right? That's what we mean by we're trying to rationalize the numerator. So we're going to multiply by the conjugate of the numerator over itself, right? Because we can multiply by 1 and it just doesn't change the value. So the conjugate would just be the square root of x plus 1 plus 2 over itself. And I'm going to show doing that here. And it has to be multiplying by 1. Don't forget to put numerator and denominator. Now the x minus 3, I think it can be helpful to put grouping symbols around the numerator and denominator here because we're thinking about distributing. But in the denominator, I do not want to multiply anything out because I want this x minus 3 to cancel, right? It's the x minus 3 in the numerator that I'm trying to uncover. So if I multiply that out, right, that's going to be x plus 1 minus 4. You think of it almost as like a difference of 2 squares factor, or you can think of it that way, right? A difference of 2 squares factored, so then multiplied together, what it would be, over, that's not what I want, x minus 3, and don't forget the grouping symbols around the square root of x plus 1 plus 2. Notice I am still using the limit notation.
Even when you do the algebra?
Huh? Yes.
Even when you, okay.
Until you use direct substitution, you have to have that limit notation.
So you just keep it back to the new.
Well, now the x minus 3's cancel. Now you could skip to direct substitution if you're comfortable with that, or I'm just gonna write out the simplified version here. But it's now when I go to substitute the 3n,
Oh, so now it's fine.
that we end up with 1/4. All right, you guys, so we're going to stop here. Your only homework from me is to look through the notes before you come to next class so that you so that you, like, of what we've already done, so that you remember what we were talking about. And you don't come in and you're like, indeterminate form, what?
What was that?
Yeah, no, we're not going to do that, right?